Individual ants have limited capabilities, but as a group, they can achieve impressive results. For example, when searching for food, now finding food is an optimization problem, meaning it's a problem of gathering food while minimizing the energy needed to do that. Now, stigmergy is where individual organisms interact with each other through modifications of their environment. It is a form of self organization that can produce complex structures and behavior without the need for planning or direct communication. Now, ants find the shortest path from colony to food source using stigmergy. They use pheromones, which is a chemical they produce in order to mark a path for other ants to follow. Now, when other ants come across a pheromone trail, they follow it with a certain probability, and this probability increases relative to the strength of the pheromone trail, and the pheromone strength increases relative to the number of ants that have followed that trail and how recent this happened. Now, ants do not always follow the same pheromone trail because some of them should always be searching for new food sources. And pheromone trails degrade over time so that ones that no longer lead anywhere stop being attractive and are replaced by other trails. So the above is the inspiration for ant colony optimization, where we are not looking for a model of real ant behavior, but we are attempting to exploit elements of ant stigmergy in order to solve similar problems. This tutorial covers solving the traveling salesman problem with ant colony optimization and Java 8. I will start with a demo of the pre-built ACO application where each city is identified by its latitude and longitude coordinates, and where the Haversine formula is used in order to calculate distances between cities, and where the application will find and display the shortest route. Second, I will step by step write, explain, and run this application using an Eclipse IDE. This is a pre-built application, so let's go ahead and run it. So we have 500 artificial ants, and we started with this route as the shortest route with ant number 2. So we start from Boston and then go to New York, then Chicago, etc. until San Francisco, and then go back to Boston. And we ended up with this route as the optimal route with this distance in miles. And this was discovered by ant number 63. Next, I'll start by creating a new project. And this will be running on Java 8. And we will initially start with 3 classes. Before adding the remaining classes. So this class will be driving the application, and it will have a main method, and we will have an ant class and a route class. Now for the purpose of this tutorial, let's define 500 ants with each of them trying to find the shortest route, and we will define this executor service. And this is an executor that provides methods to manage termination and methods that can produce a future for tracking progress of one or more asynchronous tasks. And we will have this executor completion service. It uses a supplied executor to execute tasks, and this class arranges that submitted tasks are upon completion placed on a queue accessible using the take method. And I also need to define this counter for the number of active ants, and we need to instantiate and activate each one of those 500 ants. So we will do it in this loop. We will use the executor completion service submit method, and this method takes in a callable. So let's go to the ant class and make it implement the callable interface. And by doing that, we will add this method call. And from the ant class, I will need access to the route that this ant has traversed. So we'll define this route and the get method. And also let's have a print line statement here. And going back to the driver class, now we can do a submit. And here we will instantiate a new ant. And let me instantiate a driver instance here. And we will increase the counter here. And we will have a while loop. So while we have active ants, we will call the take method on the executor completion service. And this will end up triggering a call to this method, to the call method, which would return an ant instance, and from that instance we can get access to the route associated with that ant. And in the while loop we will decrease the counter, and we will do a shutdown now on the executor service. And let's add some print line statements. And we'll have one to indicate that we submitted a new ant, and one to indicate that we did a take method on the executor completion service. So let's go ahead and test run the application before adding the remaining classes. So here we go, we entered the activate ants loop, and this is for each one of the ants. So after take is called, the call method ends up being invoked, and then we exit that loop. So let's go ahead and add this ant colony optimization class. And a city class representing a city on the route. And we also need a utility class, atomic double, and it will be in this package. Now the city class will have the exact same code as in previous traveling salesman problem tutorials that I have done. So we have three constants: the Earth's equatorial radius, and converting degrees to radians, and converting kilometers to miles. And a city is defined by its longitude, latitude, and name. And those three are initialized in the constructor. And we have get methods for all three of them. And the toString method returns the name of this city. And the measure distance method measures the distance between the passed in city and this city. And it uses the Haversine formula to do that. And the route class will have an array list of cities on this route and the total distance for the route, and get methods for both, and the constructor will initialize those two values. And the toString method will print out all the cities on this route and the total distance. And for atomic double, an operation is atomic when you can safely perform the operation in parallel on multiple threads without using the synchronized keyword or locks. So we will have this class extend the number and implement the comparable interface. And since this is a utility class, I'll just put the code that we need over here. Next, let's go to the driver class and add this initial route. Now going to the ant colony optimization class, we need two matrix here. One to keep track of the pheromone levels between the different cities, and another to keep track of the distances. And we will have get methods for both. And the cities array list will be what's in the initial route, and the size will be the size of that initial route array list. And we will have two methods for initializing the distances and for initializing the pheromone levels in both matrices. So we measure the distances between the cities using the measure distance method on the city class. And we have an outer loop and an inner loop, which allows us to pick up all combination of cities. And in this method we will randomly initialize the pheromone levels in this two-dimensional array. And to do that we have an outer loop and an inner loop. Next, let's go to the ant class, and here I want to keep track of the ant colony optimization instance we are using, and the ant identification number, and we will have a constructor that would initialize both of them, and a get method for the ant number. And let's define -1 as an invalid city index, and the number of cities will be what's in the initial route. And before continuing with the ant class, let's go here and fix this error message. So I'll have this ant colony optimization instance, and pass that instance and the ant number to the new ant we are instantiating. Let's go back to ant. Now in the call method we will start by randomly picking up the index of the originating city, and let's define an array list containing all the city on this route for this ant, and we will be returning this, and we will have a hash map for visited cities, and initially we will indicate that all the cities are not visited in this hash map, and let's define this number of visited cities and initialize it to 0, and let's indicate that the originating city is visited. So we have the originating city index here inside the visited cities hash map, and we're setting true here, and I will initialize the route distance to 0, and x will be the index of the originating city, and initially y will have -1 as index, and if we haven't yet visited all the cities, then I will have this method getY that will return the index of the next city to visit. And let's define this getY method, and let's return the invalid city index for now. We will pass it the index of the originating city and the hash map of all the visited cities, and it would return the index of the next city to visit. And going back to the call method, so if we haven't yet visited all the cities, then we will add the originating city, so driver.initialRoute.getX to the array list route cities that this ant is traversing, and we will add the distance from city with index X to city with index Y to the route distance. And next we'll call a method that adjusts the pheromone level. So this method takes in the indexes of the originating and destination cities and the distance. And next we will indicate that the city with index Y, so the name of that city, so it is visited. And next I will set the index of the originating city to be what used to be the index of the destination city. And next we will try to find another city to visit if we have not yet visited all the cities. Otherwise I will set Y to be the invalid city index, so that we can exit this while loop. And after exiting this loop, we will add the distance from the final city back to the originating city to the route distance. And since X is the last city, I will add it to the route cities. And the route associated with this ant will be a new route instance given the route cities and the route distance, and we will return this ant instance. Next, in adjust pheromone level, I will have a boolean flag and only exit this while loop if the flag is set to true. And we will initially pick up the current pheromone level between cities with index X and Y. And next I will update the pheromone level according to this formula. So Q is a parameter used for adjusting the amount of pheromone deposited, and the value is between 0 and 1, and rho is a parameter used for varying the level of pheromone evaporation, and the value is between 0 and 1. And for the purpose of this tutorial, I'll have them set to those two values. And next, if all pheromone have evaporated between cities with index X and Y, then I will set the pheromone level to 0. Otherwise, I will set the pheromone level in the matrix to the updated pheromone level. Now in the getY method, I will start by picking up a random double number between 0 and 1, and next I will pick up an array list of transition probabilities, and those would be the probabilities of moving from a city with index X to the other cities. So I need to define this method. So we will have this array list transition probabilities that we will end up returning after populating it. Now going back to the getY method, let's go ahead and add this logic. So we would go through all the cities, and if the transition probability of city with index Y is bigger than a random number, then this will be the index of the destination city. Otherwise, we would modify random and go back into the loop, trying to find a different destination city. And now coming back to this method, I will initialize all the transition probabilities in this array list to 0. And before finishing this, let me define two methods. Get the transition probability denominator, and we'll define this denominator and end up returning it. And get the transition probability numerator, and we'll define this numerator and end up returning it. So here the denominator will be what's returned from this method. So I will pass it the array list of transition probabilities and the index of the originating city and a hash map of visited cities. And I will set all the transition probabilities in this array list according to this formula. Now here I will have this logic So we will go through all the cities, and if the city has not been visited, here we make sure that we are not moving from and to the same city. Otherwise, we will set the transition probabilities to what's returned from this method. And here we are adding that transition probability to the denominator. And in this method, this is the logic that we need to add. And let's come back here and define alpha and beta. So alpha is the parameter used for controlling the importance of the pheromone trail, and the value is bigger or equal to 0. And beta is a parameter used for controlling the importance of the distance between source and destination, and the value is bigger or equal to 1. So here I am picking up the pheromone level from the pheromone level matrix between cities with index x and y, and if that pheromone level is different than 0, then the numerator will be set according to this formula. This should do it for this class. Next, let's go to the driver class. And here let's start by defining this processing cycle probability that I will be using shortly. And this route, and we will start the main method with a print line statement indicating the number of ants that have been activated. And let me remove this print line. And we will have this print heading method that will print the heading row, so the route, the distance in miles, and the ant identification number. And after instantiating the driver, we will do a print heading, and let's add this process ants method, and we will move the while loop down there, and we will do if pick up a random number, and if it's bigger than the processing cycle probability, then we go ahead and call the process ants method. And here let's take out the driver since we don't need it, and let's rewrite this executor completion service dot take. So we pick up an ant, so what take returns is a future, so that future we do get on it, and so when take gets called, what ends up being called is this call method, which returns an ant. And And up here, before doing the shutdown now, we'll call the process ants again to finish up all ants that haven't been processed yet. And we will pick up the route that was traversed by this ant. So ant.get route. And if the distance for the current route is smaller than the distance for the shortest route, the shortest route becomes the current route. And then we do a system.out.println for the cities in the shortest route and the distance that we prepare over here, and the ant identification number that found this route. And after the shutdown now, let's go ahead and add these two println statements. So the optimal route and the distance of that optimal route. Finally, let's go ahead and test run this application. So ant with identification number 1 found this route starting from Austin, going to Houston, etc. until getting to Boston, and then going back to Austin. And it had this distance in miles. And ant with identification number 267 found the optimal route, and it has this distance in miles.